Hi! In this class, we are going to have a bird's-eye view on the available SDAccel optimizations. All the presented optimization can be also found in the SDAccel Environment Optimization Guide provided by Xilinx and available online. Obviously, the optimization presented here are not the only available ones, but they are more a list of recommendations to optimize the performance of an OpenCL application that have to be used as a starting point for ideas to consider or investigate further. Within this context, I'd like to organize these recommendations in three sets of optimization: arithmetic optimizations, data-related optimization, and finally, last but not least, memory-related optimizations. Arithmetic optimization are related, as the name is suggesting, to the possibility of exploring optimization by means of using optimized math functions, and in the case of the built-in math function from HLS math library, or by exploring optimized implementation by using specific data representation, as in the case of fixed-point arithmetic. Data-related and memory-related optimization are much more blurry in the sense that some data-related optimization can have some memory-related aspects, impacts, to make totally fair to consider them as also memory-related optimizations. Said that, just for the sake of simplicity, I still like to have this high-level distinction, and in considering data-related optimization as specific optimization on data and computation, while as memory-related optimization, recommendation on how to work with memories, interfaces, and data transfer. Data-related optimization can be divided in two optimizations: choosing optimal workgroup size and in being able to isolate data transfer and computation. Finally, memory-related optimization are used to exploit, at the best, memories and memory bandwidth utilization, and to transfer data efficiently by using specific commands, like the clnq migrate mem objects. Let us now explore a little bit more these optimization recommendations, starting from the arithmetic ones. The first recommendation is to use optimized built-in math functions from the HLS math library. OpenCL specification provides several math built-in functions, and we can gain advantages out of them. All the math built-in functions with the native prefix are mapped to one or more native device instructions and will typically have better performance compared to their corresponding functions, the ones without the native prefix. In the Xilinx SDAccel environment, this native built-in function exploits the equivalent function in Vivado HLS math library. Now, this is where the benefits of using built-in math function comes into play, and this is because the function in the Vivado HLS math library have been already optimized for Xilinx FPGAs in terms of area and performance. It's important to notice that the accuracy, and in some cases the input range of these functions, is implementation defined. Therefore, it's important to verify that the accuracy meets the application requirements, but once this is done, it's definitely recommended to use native built-in functions. A second optimization can be obtained by exploring fixed-point arithmetic. This is the eternal fight in between fixed and floating-point computations. In both cases, we are referring to the corresponding manner in which numbers are represented. On one hand, by using fixed-point representation, we are fixing the number of digits with respect to the decimal point. On the other hand, with the floating-point representation, the placement of the decimal point can vary, float, relative to the significant digits of the number. Within this context, just to name a difference, floating point can support a wider range of values with respect to a fixed point representation, with the ability to span from very small numbers to very large ones. Now, because of this, some applications use floating point computation, but all these benefits in using floating point arithmetic comes at a cost. Managing floating point representation is more complex if compared to fixed point arithmetic. Within this context, it may happen that using fixed-point arithmetic can save the power efficiency and area significantly while keeping the same level of accuracy, as it can be the case of some deep learning algorithms. As deep learning inference exploits lower bit precision without sacrificing accuracy, it can be convenient to explore alternative implementation, such as the int8 deep learning operations implemented on the Xilinx DSP48E2 slice, rather than using right away floating-point arithmetics. Therefore, the general recommendation before coming to using floating-point operation for your application is to explore fixed-point arithmetic first. Before continuing, if interested in knowing more about deep learning and on how to efficiently use fixed-point representation, I'd like to suggest you to read the Deep Learning with int8 optimization on Xenix devices white paper. Let us now see the impact of being able to choose the optimal workgroup size. As we know, OpenCL computational model is built around the logic abstraction of work item and workgroup. Just as a reminder, a work item is the basic unit of work within an OpenCL device, while a workgroup is a group of work items. Within an OpenCL code, OpenCL computational model requires the user to specify both the global size, an example the n-dimensional size of the total number of work items, and the local size, the n-dimensional workgroup size, and by doing this, we will give the compiler more flexibility to optimize the size of the kernel. Global and local size can be 1D, 2D, or 3-dimensional, according to the dimensionality of the problem to process, and this means that OpenCL can process, at most, 3D problems. The next optimization I'd like to introduce is the isolation of data transfer and computation. This is not really an optimization, but it's more a kind of recommendation. Being able to separate the kernel computation from the corresponding communication infrastructure to transfer data is quite important to be able to optimize them both. Separating out the two will help you to better understand where to begin your optimizations. To better understand the performance of your kernels, it's crucial to be able to isolate either the data transfer or the computation to focus on the specific potential kernel optimization, or to be able to use simple control structures in the read-write function, which makes burst data transfer detection simpler. Finally, last but not least, we can explore the memory-related optimization suggestions. We can summarize them as in the following list. Using the CL&Q migrate mem objects to transfer data, avoid complex structure or classes for kernel arguments, using on-chip memories, and maximizing the utilization of global memory bandwidth. The CL&Q migrate mem objects command, as we can read in the SDAccel environment optimization guide, migrates memory object explicitly perform ahead of the dependent commands. This allows the application to preemptively change the association of a memory object through regular command queue scheduling in order to prepare for another upcoming command, and it also allows application to overlap the placement of memory objects with other unrelated operations before these memory objects are needed, potentially hiding transfer latencies. Avoiding complex structure or classes for kernel argument is quite crucial because, as we know, kernel arguments are mapped onto hardware interfaces between the host code and the FPGA. This means that complex structures or classes can lead to very complex hardware interfaces due to memory layout and data packing differences. Using on-chip memories can improve the efficiency and performance of an accelerated application. This is because acceleration platforms supporting an SDAccel environment can have as much as 10 MB on-chip memories that can be used as on-chip global memories, pipes, local and private memories. Finally, efficient data movement between the kernel running on the underlying FPGA device and the external global memory is critical to the performance of accelerated applications. Having the best implementation ever from a computational perspective running on the FPGA without being able to efficiently read and write data from external DDR's RAM, as an example, is going to end into a useless design. A well-designed kernel minimizes memory accessing latency while maximizing the usage of the available data bandwidth provided by the acceleration platform. That's why using burst data transfer, using full user data width of memory controller, and using multiple DDR banks are considered key optimization and deserve a specific class to be presented.